So sequence is nothing. It is actually a function. So if you read the definition, informal definition of sequence, you can see that. Okay, you can see that for each positive integer n, for each positive integer n, okay, for each positive integer n, okay, so for each positive integer n, okay, so each positive integer means natural numbers. Okay, for natural numbers, okay, so we are given a real number. We are given a real number. Then such numbers, okay, then this list of number, we call it as the sequence. This list of number, we call it as the sequence. Okay, so there are many ways of writing a sequence. Okay, either we can write listing out all the elements, the first two elements, and like this, or either we can use the round brackets, or we can use a curly bracket. You know, some in books you may see that the sequences are written using this notation also. Okay, so whatever the notation, so in this course we'll use this notation. Okay, we'll use this notation to denote a sequence. Okay, right. So now let's have the formal definition of sequence. Okay, so formal definition of the sequence is like this. So sequence is nothing. It's a function from set of natural numbers to set of real numbers. Okay, sometimes it can be set of complex numbers. Okay, set of complex numbers. So in that case, we say sequence as complex sequence. Since the codomain is real number, this is our real analysis course. Here we will be we will be talking on set of real numbers. Okay, we will be talking on set of real numbers. So that is why it is called the sequence of real numbers. Okay, so it's a function. It's a function from natural numbers to set of real numbers. Say for an example, if I define the function like fn is equal to 1 over n, so like we are using the function fx. Okay, here I am using the letter n instead of x because the domain is natural number, set of natural numbers. Say, so for an example here, I have written a function 1 over n. So here n belongs to set of natural numbers. Okay, so n belongs to set of natural numbers. So when you put values for n, say for example, if you put 1, then the first number of this sequence is 1. If you put 2, the second number of this sequence is half. If you put 3, the third number of the sequence is 1 by 3, and it goes like this. So this is a sequence. Similarly, another one can write another sequence. Say for an example, fn is equal to, I say 2 over 2 to the power n. So this is also a sequence. This is also sequence. So if you write this sequence, then if you put n equal 1, the first number is 2. If you put n equal 2, the second number is 2 squared. If you put n equal 3, then that is 2 to the power 3, and so on. So likewise, we can write our own sequence and work with those sequences. Okay, here are some examples for sequence. Here, the first sequence is defined in this way: a(n) equal 1 for all n belongs to natural number. So this is called the constant sequence, because in this example here, whatever the number you put, all are 1, 1, 1, and it goes like this. Therefore, this is called the constant sequence. Second example, if you look at the second example, it is a(n) with a(n) equal n. So this is the general term of the sequence. We are here. We are writing the general term of the sequence in this form. So if you put n equal 1, 1, then the second one is 2, the other one is 3, the other one is 4, and it goes like this. So that is the sequence, second example. So this is also sequence. The third is actually here, as I explained here. Third one is. The fourth one, if you look at the fourth one, if you put n equal 1, the first one is 1 over 2. Then the second one, 2 over 3. And if you put 3, that is 3 over 4. Okay, so it goes like this. And the fifth one, the last one, if you look at the sequence, okay, look at the last one, actually it is minus 1 to the power n. If you put n equal 1, if you put odd natural number, then the first number will be minus 1. Then the second will be minus 1 to the power 2, which is equal to plus 1. Okay. Then next one is minus 1. Then next one is plus 1. Then it goes like this. So this is the sequence. Okay. So if you look at the last one, it takes the values 1 and minus 1 alternatively. Alternative means one after the other. One after the other. So these are few examples for sequences. Okay. Right. So now we are going to talk about the convergence and divergence of this. Actually, we studied this in the last class. I don't want to repeat these things. Okay. So I'm just quickly go through this and we'll start today's session. Okay. So here, if you look at the first example, so convergence is one of the fundamental concepts, because when you have a sequence, okay, we cannot miss talking the convergence of the sequence, because most of the properties of a sequence depends on its convergence. Okay, depends on its convergence. Okay, therefore it is important to talk the convergence of the sequence. Okay, so before we look into the formal definition of what is convergence, okay, and divergence, we'll have some example. Okay, so you just observe what happens as n gets larger and larger. Okay, so in this one, if you take the first example, whatever the value of n, the value of each term of the sequence is 1. So as even the n becomes larger and larger, okay, n becomes larger and larger, okay, regardless of the value of n, the sequence is 1. Okay, this sequence is 1. You just observe before we go to the formal definition. If we go to the second example, that is, as we heard, first term is 1, the second term is 2, third term is 3. So what is happening here, as n gets larger and larger, okay, the value of the sequence also becomes larger and larger. Okay, becomes larger and larger. And if you look at the third one, what is happening? The first term is 1, the next term is half, okay, the next term is 1 over 3. So as n increases, what is happening here? The sequence tends to 0, isn't it? Because the denominator becomes larger and larger, the sequence gets to 0. Okay, here also you can observe that. You can observe that when n becomes larger and larger, this sequence gets closer to 1, because if you put n equal 1, the first term is half. If you put 2, then this becomes 2 by 3. Okay, so it is increasing, and finally it gets closer to 1. Okay, so but this goes to infinity actually. Okay, but whatever the thing, this one goes to 1. Goes to 1 in the sense all the values are 1, no? So it is happening here. But here, what is happening? Minus 1. First term is minus 1. The next term is plus 1. Next term is minus 1. So we cannot conclude whether it goes to plus 1 or minus 1. So it doesn't go, we cannot determine this one. Sometimes it goes to plus 1. Sometimes it goes to minus 1. Okay, so we cannot determine this one. So that is why it says it doesn't come closer to any number, because sometimes it may goes to plus 1, sometimes it goes to minus 1. So it oscillates between plus 1 and minus 1. So actually, convergence means, in informal terms, convergence means the property of the sequence, the property of the sequence as n becomes larger and larger. Or convergence means, okay, what happens? Convergence means what happens to the sequence when the value of n becomes larger and larger. Okay, now we are going to have the formal definition of the convergence. Okay, a sequence an in R, that means the real sequence is said to be converged to a real number a. So we are saying that the sequence an the sequence an converge to real number a. That means that when n tends to infinity, the value of this sequence becomes a. Here, as it comes to 1, here the value of a is equal to 1. Here, the value of a is equal to 0, like that. Okay, so here we say that this sequence converges to the real number a if for every epsilon greater than 0, there exists a positive integer n in general depending on epsilon. That means that when you have a different epsilon, when you choose different epsilon, the value of n may vary such that mod of a n minus a less than epsilon for all n greater than capital N. Okay, for all capital N. In that case, the number a is called the limit of the sequence. Okay, so here we are having 3 definitions. So this is for convergence. This definition is for convergence. This number a is called limit of the sequence, and we say that the sequence an is convergent. Okay, in that case we say that sequence an is convergent. Okay, so this is the definition. Normally this is the definition. This definition is called epsilon n definition. Okay, this definition is called epsilon n definition. Okay, so in the exam they may ask you to use epsilon n definition to show a particular sequence is convergent. Okay, particular sequence is convergent. So in that case, you have to use this definition. Okay, you have to use this definition to show that the given sequence is convergent. Okay, there are some examples later. You can understand, you can see how we can show a particular sequence is convergent using this epsilon n definition. Okay, so the idea is here. It says that whatever the epsilon you choose, there should be a natural number. There should be a natural number capital N such that this an minus a should be less than epsilon for all n greater than or equal to n. Okay, so that is the thing. So here there is a note here. Look at the note here. Note that the different epsilon can result in different n. As I told you before, if you choose another one epsilon, then the value of n may be 1. If you choose another epsilon, that will be another one. Okay, so we shall illustrate this in example 2.2. So there's example 2.2. So we'll discuss that in a few minutes. Okay, so this is the notation. If a sequence an converges to a, then we write limit n tends to infinity an equal a, or we can simply say an tends to a as n tends to infinity, or you can simply say an tends to a. So there are 3 different ways of writing a sequence converges to a. Either you can say limit n tends to infinity an equal to a, or you can say an tends to a as n tends to infinity, or you can say simply an tends to a. So these are 3 notations for saying the sequence an converges to a. Okay, so sometimes this definition may look somewhat complicated and you may find difficult to understand. But if you have an example, then you can easily understand. I think I explained this in the last class also, but anyway, I I explained this once more. Okay, so look at this definition. I'm telling it again. A sequence, you have to read word by word. A sequence an in R is said to be converged to a real number. Okay, real number for all epsilon greater than 0, there exists a positive integer n such that mod of an minus a is less than epsilon. That means that say this is your sequence. I'm explaining here. Okay, look at this one. So I'm using this one to explain. Okay, right. So you have the sequence a. Say for an example, this is your sequence a. Okay, this is your sequence a. Then if you list out this one, this is actually nothing. The first term is a1, the second term is a2, then the third term is a3, and it goes like this. Okay, it goes like this. Right. So this is your n value. Say this is your n. When n equal 1, sequence is 1, n equal 2, this is 2, then n equal 3, this is, and it goes. It's an infinite. There are infinite number of terms in this sequence. Now we say that this sequence AN, okay, this sequence AN converges to A, converges to A. Then it says that for all epsilon, okay, for all epsilon greater than 0, there exists capital N belongs to set of natural number such that what is the condition? It says that mod of AN minus A. Look at A. A is the limit value of the sequence. Okay, limit value of the sequence is less than epsilon whenever or for all n greater than or equal to n. This particular n, these two are same n. Okay, these two are same n. Okay, let me erase it and use another color. There is n, okay, the same n here, the same n. So if AN converges to A, then the definition says that for all epsilon greater than 0, there is a natural number n such that, so that means that in this sequence, okay, in this sequence, there is a natural number here. Say for an example, your n is here, your n is here. So say this is AN, okay, AN. So this one is n plus 1. Okay, so this is AN plus 1. And it goes like this. Okay, it goes like this. So it says that if you choose an epsilon, then from this point onwards, for all these sequence, if you calculate the value of AN minus A, okay, that will be less than this epsilon value. This epsilon value. So this will be less than this epsilon value. So if you choose another epsilon, then there may be a point here. There may be a point here. Okay, there may be a point here. If you choose another epsilon, then there may be a point here. There may be a n here. For these value, these sequences, this condition here. Okay, so that is what it says. So this inequality will hold for n greater than, for all the n greater than this particular n. Okay, this particular n. So that is why it says. Say for an example, let me explain this using an example. Okay, right. So now let me take as an example. Please listen to me carefully. Say let me take my AN, my sequence B 1 over n. Okay, this is my sequence. I know that this sequence tends to 0. This sequence tends to 0 as n tends to infinity. I know this one. Okay. Therefore, my A is equal to 0. The limit value of this sequence is A. 0. Okay. So now, okay, look at here. If I choose an epsilon, say for an example, so I'm writing my AN here. My n is here. So my AN, if I write my AN, first number is 1, second number is half, then third number is 1 over 3, then 1 over 4. Okay, so my n is, first number n is 1, the other one is 2, the other one is 3, the other one is 4, and it goes like this. Okay, right. Now I'm choosing my epsilon as 2. Look at this cap. I'm choosing my epsilon as 2. Okay, if I choose my epsilon as 2, If I choose my epsilon as 2, okay, let me choose my epsilon as half. Very simple example. Let me choose my epsilon as 0.5. A very simple number, 0.5. Then you just calculate an minus a, an minus a. So an minus a is nothing but 1 over n minus 0, which is equal to 1 over n. So here I am writing my an minus a. So an minus a is nothing but 1 over n, mod of 1 over n, which is same as 1 over n. Okay. Because my a is 0 here. Look at here carefully. My a is 0 here. Therefore, I am going to write that also. Okay, I am going to write that also. So an minus an is nothing but 1 over n. Therefore, the first one is 1, the other one is 2, the other one is 3, 1 over 3, and it goes like this. Okay, it goes like this. Then you see that my epsilon was, let me choose my epsilon as 0.5. Let me choose my epsilon as 0.5. Then you see that there is an n. Say for an example here, there is an n. So this is your capital N. This is your capital N. So now from this n onwards, if you look at the next element here, you can notice that your next element is what? 1 over 4. The next element is 1 over 5. The next element is 1 over 6. So if we choose epsilon equals 0.5, if we choose epsilon equals 0.5, in this n, you can see that there is a n. After all these, this value, if you look at these values, okay, if you look at these values, these all values, okay, if you look at all these values, let me erase this. Right. So if you choose epsilon equals 0.5, you can see that an minus a, the value of an minus a, from 3 onwards, it is less than the epsilon. You see, all these values are less than 0.5. So we are saying that there is a n, okay, for which from that point onwards, all the values of mod of an minus a is less than 0.5. Okay, so there is a n. Now, if somebody choose, say for an example, epsilon equal to say 0. Say let me say 25. If somebody choose epsilon equals 0.25, then you can see that if epsilon equals 0.25, then you see that from here onwards, okay, from this point onwards, here this is 5 now. From this point onwards, okay, from this point onwards, you see that from this point onwards, all these values. Now your n is this one. Now your n is this one. For this epsilon 0.5, now the n is 5. If you choose n is equal to 5, all the values of an minus a, mod of an minus a, after n equal 5, you see that these values are less than 0.25. Isn't it? So when you choose different epsilon, there will be a n. All the values after that n, the value of this mod will be less than that epsilon. Then we say that that sequence is convergent. So meaning that, what is the meaning of this one? Whatever the epsilon value you choose, even if you choose 0.0000001, okay, then definitely you can find an n such that an minus mod of an minus a will be less than this value. So what is the meaning of that? That means that the an gets closer and closer to this a. So that means that finally an tends to a. So this is the definition. This is the meaning of, this is the explanation of this definition. Do you understand? Do you understand, students? Can one of you answer me, please? Hello? Can you answer me, please?
Yes, sir.
Okay. So if you have any questions, you can use the chat box to ask me. Okay. Otherwise, online, we don't know whether you are really in the class. Anyway, right. So you understand the meaning of this one. You understand the meaning of this one. Now we are done this one. So if a sequence converges, either we use this notation. Okay, thank you. Okay, either we can use this sequence, either we can use this way or this way or this way to write to denote that the particular sequence converges. Okay, now let's have some example. Okay, let's have some example. The sequence 1 over n minus 1 over n over n 1 minus 1 over n are convergent with limit 0, 0, 1. So this sequence, this converge to 0. Okay. This also converge to 0. This also converge to 1. This also converge to 1. So these all are convergent sequence. Now we are going to use, or we are going to prove that, or we are going to justify that they really converge to, they are really convergent sequence. Okay, this is the important part. Okay, this is the important part. Now here in this example, if you look at this one, my example was an equal 1 over n. So when I choose epsilon equals 0.5, I found that my capital N is equal to 3. When I choose epsilon equals 0.25, I found the capital N was 5. If I choose epsilon equal 0.625, okay, so then what is my capital N? If I choose epsilon equal 0.1, what is my capital N? Then it's a problem. We cannot list out all the terms of the sequence. We cannot find mod of a n minus a, and then we cannot, it is not practical to determine, for what value, from which value of n onwards this condition, that is mod of a n minus a less than epsilon holds. We don't, it is not practical writing all the terms of the sequence and calculating this value and finding out the capital N. Therefore, here this is not the way of showing. This is not the way of showing that. The particular sequence is convergent. Okay. Therefore, we have to directly use, or we have to use some more general proof. Here, actually, we are listing out all the elements and we are trying to show that from this n onwards, for this particular epsilon, all these value will be less than epsilon. So that's not practical always. Therefore, what we are going to do is, we are going to show in general, okay, from this point onwards, the sequence will be the capital N. From this point onwards, the condition will hold. Okay, now look at this one, the first example. So if you can understand the first one, the rest of the things are similar. Okay, the rest of the things are similar. Definitely you will get a question, one question for your final exam like this. I'm not saying one of this question, but definitely you will get one question for your final exam like this. Okay, so this is if you look at this one, all are similar. All are similar. If you understand the concept, this is very similar. Okay, right. So now I'm explaining this one. Look at this one. Let an equal n. Let an equal n. For all n belongs to n, let epsilon be given. Okay, now look at here. Now my sequence an is equal. I'm using this here, then you can understand. You can read this one and understand later. Okay, I'm explaining using a whiteboard here. Then you can easily understand later. So my sequence an is equal to 1 over n. This is my sequence. Okay, this is my sequence. An is equal to 1 over n. Okay, now what we want to show is, okay, what we want to show is here. Look at here. For all n belongs to n, let epsilon be given. Okay, then we have to identify an n belongs to n such that 1 over n is less than epsilon. So look at the definition. If a sequence an, okay, if a sequence converges to a, if look at here, if a sequence an converges to a, then what's the definition? For all epsilon greater than 0, for all epsilon greater than 0, their x is capital N belongs to set of natural number such that mod of an minus a is less than epsilon for all n greater than or equal to capital N. These two are same. Okay, these two are same. Look at here. This n and this n are same. Huh? Okay, this n are same. Right. Now, this is what we want to show. Now we want to prove that. Now we want to prove that this an, that is, now we want to prove that our an, which converges to 0. So this is our a value. This is the value of our a. Okay, so this is our a. So we want to show it. We want to show this one. When an equal 1 over n, when an equal 1 over n, when an equal 1 over n, that obviously when n tends to infinity, what happens? What happens to this one? So as n tends to infinity, 1 over n tends to, obviously this tends to 0. We know that, isn't it? This tends to 0. So we want to prove that one. So our a is equal to 0. So what we have to do is, we have to, whatever epsilon, we want to show that there is a corresponding n. There is a corresponding n which satisfies this condition. That is what we want to show it. Telling this again clearly. If you want to say an tends to infinity, then what we have to show, for all epsilon, for whatever the epsilon, there is a n. Okay, there is a n belongs to n such that mod of an minus a is less than epsilon for all n belongs to a. Therefore, now we want to show an tends to 0 means we want to find out. So we want to find capital N. We want to find capital N belongs to set of natural number such that for all epsilon greater than 0, whatever the value of epsilon, mod of an minus a. My an is what? 0 is less than epsilon. Okay, for all n greater than or equal to n. So we want to find out this one. Okay, so we want to find this n. So if we can find that n and say that, then that's enough. Okay, so here, so we'll try to find out this n. We'll try to find out this n. Then you can understand. Right. So now, actually, we are going to we are going to work backward. Okay, right. Look at here. Look at the proof carefully. Look at the proof carefully. So now, so we are checking any epsilon. Let epsilon greater than 0. Let epsilon greater than 0. We are taking any epsilon. Okay, so we have to prove for any epsilon. So let epsilon greater than 0. Look at the proof very, very carefully, yeah? Because definitely you will get a question for your final exam. So let epsilon, I'm taking an arbitrary epsilon here. I'm taking an arbitrary epsilon here. Okay, then we can say that, 1 over epsilon is less than n. Less than n. So you can say that 1 over epsilon is less than, so you can say, wait a minute, I'll tell you again. Then let epsilon greater than 0. Okay, let epsilon greater than 0. Then so let epsilon greater than 0. Look at here carefully. Let epsilon greater than 0. Then you can say that, okay, you can say that here, look at the proof here. You can say that 1 over n less than epsilon. Why? Then you can say that 1 over epsilon less than epsilon. Why is that? Why is that? 1 over epsilon less than epsilon. Why? For some n belongs to n. Why is this? Actually, we know that Archimedean property. What does the Archimedean property says? What does Archimedean property says? So can you remember the Archimedean property? We studied in the chapter 1. Archimedean property says what? If x belongs to R, I'm telling the Archimedean property again here. Actually, we are doing this based on the Archimedean property. If x belongs to R, if x is a real number, if x is any real number, then there exists nx belongs to set of natural number such that what? This x is less than nx. That means that if you have a real number, definitely you can find a natural number which is greater than that particular real number, isn't it? That particular real number. So this is called the Archimedean property. So if x belongs to R, then there exists a natural number nx belongs to n such that this x is less than nx. So here, look at the same way. Epsilon greater than 0. Epsilon can be anything. So epsilon, I'm choosing as a so epsilon is a real number. Epsilon greater than 0 means it is a real number, any number. It can be a decimal or whatever it is. It can be a number. Okay, then obviously 1 over epsilon is also a number. 1 over epsilon is also a number. Then using the Archimedean property, you can say that 1 over epsilon is less than n for some n belongs to n. So this is actually coming from Archimedean property. Okay, so this is actually coming from Archimedean property. That's why I said Archimedean property may looks very simple, but there are so many applications of Archimedean property. So we are taking any epsilon greater than 0, then we can say that 1 over epsilon is less than n for some n belongs to n. Why? Because for each real number, you can find a natural number which is greater than that real number. Okay, so from this one, you can write it, since it's a positive number. So epsilon is a positive number, therefore 1 over epsilon is also a positive number. 1 over epsilon is also a positive number. Therefore, you can write this as 1 over n, okay, less than epsilon. Because I'm just having a cross multiplication or something. Okay, I'm just multiplying this here and multiplying that here. Oh, you multiply epsilon by both sides and then 1 over n by both sides. Then you can have this inequality. So from this one, you can have this inequality. Okay, from this one, you can have this inequality. So you see that 1 over n, 1 over n, now we are having this one, 1 over n less than epsilon. 1 over n less than epsilon. Okay, so 1 over n epsilon, 1 over n less than epsilon. Okay, so 1 over n is less than epsilon if and only if n equal to greater than 1 over epsilon. Okay, so now if you take, okay, if you take, look at here, if you take your capital N as, if you take your capital N as, okay, if you take your capital N as 1 over epsilon, okay, I will tell the meaning of this bracket, 1 over epsilon plus 1. Okay, so plus 1. Then what will happen here? Look at here. Thus, if you take n as 1 over epsilon plus 1, then what we have actually? What we have? 1 over n is less than epsilon. 1 over n is less than epsilon because here this is called, this one is called the integral part of integral part of 1 over epsilon. For example, because epsilon is any value, you know, so it can be 0.1, 0.5, whatever it is. Therefore, say for an example, if your 1 over epsilon equal to, if your 1 over epsilon is equal to say 1.5, if 1 over epsilon is equal to 1.5, then 1 over epsilon, integral part of 1 over epsilon is 1. Integral part means integer part of this number. What is the integer part of this number? That is 1. Okay. Say for an example, if 1 over epsilon is equal to, if 1 over epsilon is equal to 2, then the integral part of 1 over epsilon is what? That is also 2. Because integer part of a number. Then if you choose n as this number, integral part of 1 over epsilon, okay, integral part of 1 over epsilon plus 1. I'm telling why is that. Okay, I will tell why is that. So if you choose like this, then what you can say? Simply, here look at mod of an minus 0. For the given equation, our an is what? For the given equation, our an is 1 over n. Okay, so this is equal to mod of 1 over n minus 0. Our a is 0 here. Actually, 1 over n is a positive number, therefore you can just put 1 over n. Okay, this is less than epsilon. When this will be less than epsilon? This will be less than epsilon for all these values, for all n greater than or equal to this capital N. This capital. If you choose this, then you can say that. An converges to zero. So you can say that A converges to 0. So if you don't understand, let me take an example here. Okay, here, look at here. The previous example, I'm taking An as 1 over n. My An is 1 over n. Then, if I write my An, okay, this is 1 half 1 over 3, 1 over 4, and it goes. So my n is here. I'm putting the n value here. 1, 2, 3, 4, and so on. Okay. Now I am going to calculate mod of an minus 0, which is equal to, I know, 1 over n, because mod of 1 over n is same as 1 over n. So it is same as 1 half 1 by 3, 1 over 4. Now, let me choose my epsilon as 0.5. Let me choose my epsilon as 0.5. Then, if you choose your capital N as, okay, integral part of 1 over epsilon plus 1. Integral part of 1 over epsilon plus 1. So, what does it mean? Integral part of 1 over 0.5 plus 1. So, this is actually integral part of 2 plus 1. So, this is actually 3. This is actually 3. So, you see, when if you choose n equal 3, okay, if you choose n equal 3, you see that when n equal 3, you see that from n equal 3, okay, all these values are less than your epsilon value, which is equal to 0. Okay, which is equal to 0. Say, say your epsilon is equal to, say for an example, you are saying your epsilon is equal to 0. Say 0.75. Okay, epsilon is equal to 0.75. You are choosing epsilon equal to 0.75. Then n is equal to, you can say 1 over epsilon plus 1. Then this is equal to 1 over epsilon means you can write this as 3 over 4. You can write this as 3 over 4. So therefore, if you substitute it here, this becomes 4 over 3 plus 1. So integer part of 4 over 3 is 1 actually, because this is 1.33 something. No? So integer part of this number is 1 plus 1. So which is equal to 2. So it says that for all n greater than 2, for all n greater than 2, you can see here 2 onwards. You can see that. I'm choosing another color. So you see that this is your capital N now. Okay, now your capital N is 2 now. So if you look at here, for all these values, you consider all these values are less than epsilon, which is equal to 3 by 2. Okay, so which is equal to 3 by 2. So if you choose n like this, 1 over epsilon plus 1, then that will be your n. Okay, that will be your n. So for all that value, for all the values from that onwards will be less than epsilon, Okay, so that is the proof here. That is what it says here. So I am explaining this again. Please look at this carefully. Let an equal 1 over n. For all n belongs to n, let epsilon greater than 0 be 0. So we are choosing any epsilon. We have to identify an n. So that is why we want to find an n. So if you give an n, then that's enough. Such that 1 over n is less than epsilon. 1 over n less than epsilon means why we have just written 1 over n less than epsilon. Actually, how it is coming? It is actually coming from this one. Okay. So my sequence A is 1 over n minus 0. Okay, less than epsilon. So 1 over n minus 0 is actually 1 over n less than epsilon. Since it's a positive number, we are writing it as 1 over n epsilon. Okay, actually, it's actually short. Okay, actually, properly you have to write like this, but this is also correct. Okay, so this is actually it is coming from this version. Okay, so we have to identify n belongs to n such that 1 over n should be less than that epsilon for all n greater than. So if you find a, if you give a formula, if you give a formula for n, if you give a formula for n such that this condition holds, then that is enough. So from Archimedean property, we know that from the Archimedean property, we know that if epsilon is greater than 0, then 1 over epsilon is less than n for some n, for some n. Therefore, from this one we can say that, from this one we can say that 1 over n will be less than epsilon when less than 1 over n. Okay, so we have to choose this n. We have to choose this n. So we have to choose this n. So here it is coming from here. So 1 over n epsilon. So from Archimedean property, we know that 1 over epsilon is less than n for some n, for some n. So this implies 1 over n less than epsilon. So if we choose n like this, then definitely you can say that this inequality holds. You can write this one. This inequality holds for all n greater than n. But here, look at here, n is a positive, n is an integer. That is why we are taking the integral part. Okay, n should be a positive integer because n must belongs to set of natural numbers. That is why we are taking n as 1 over epsilon plus 1. Okay, so here is here what this bracket x denotes the integer part of x. Okay, hence we can see it. So if you can find that n, then you can write this statement and simply say that that converges to 0. Okay, so if you don't understand, look at the second example. Yes. So let a n equal minus 1 to the power n. Okay, here also we want to show that here this sequence also converges to 0. We want to show that this sequence also converges to 0. Okay, that is what we want to show it here. So to show that sequence also converges to 0, actually what we have to do? We have to show that minus 1 to the power n over n, isn't it? Minus 1 to the power n over n minus 0 less than epsilon whenever n greater than or equal to capital N. So we have to identify this capital N. If you can identify this capital N and say that's enough, that's end of the proof. So that here we are saying that let a n equal minus 1 to the power n for all n. Look at the way here. We are writing the same thing. We are writing the same thing. Okay. We are taking epsilon greater than 0. Epsilon greater than 0. Since we know that mod of a, because if you look at this function, okay, if you look at this function, a n mod of a n equal to, okay, so minus 1 to the power n over n, minus 1 to the power n over n. So this is actually nothing but mod of 1 over n, because minus 1 to the power n means plus or minus it is plus 1, no? So mod of minus 1 to the power n is always equal to 1. Therefore, so mod of a n is equal to 1 over n. So finally what is happening here? It is similar to this one. It is similar to first one. It is similar to first one. So we can choose the same n and we can do the same proof and we can say that that converges to 0. Okay. So this is same as earlier because when you take the mod, it becomes 0. Now look at the last example. 1 minus n minus 1 over n tends to 0, tends to 1. Now we have to prove that this tends to 1. So here actually what we want to do is, here what we want to do is, okay, so we have to find out the n. So we have to find n. So we have to find n such that mod of an minus 1. This time 1. Because why? Because we know that when n tends to infinity, okay, limit 1 minus 1 over n as n tends to infinity. Okay. N tends to infinity, what will happen? This is equal to 1. So the limit value of this sequence is 1. Therefore, what we want to prove actually, an minus an less than epsilon whenever this n is greater than or equal to that capital N. So we want to find out this capital N. We want to find out this capital N such that this inequality forms. Okay, so here we are taking an is this way and we are taking let epsilon greater than 0. Then an minus 1. So an minus 1 mean what? So an minus 1 mean what actually? So if you look at here, an minus 1. If you try to find this an minus 1, this is nothing but 1 minus 1 over n minus 1. Isn't it? 1 minus 1 minus 1. So this is nothing but minus 1 over n. This is nothing but 1 over n. So finally, the third one also comes in the form of the first one. Therefore, again, if you use the same argument using the Archimedean property, then you can say that if you choose your n as 1 over epsilon, the integral part of 1 over epsilon plus 1, then from that point onwards, this whatever the epsilon, from that point onwards, this inequality will hold. So that is what here we are trying to see. Okay, that is what in here we are trying to see. Say for an example, if you want to understand that here, let me take here your an is, here look at your an. Your an is equal to, okay, 1 minus 1 over. This is your an. So let me write an for some values. So an is equal to, say if you put n equal 1, then that becomes 0. If you put n equal 2, that becomes half. If you put n equal 2, it becomes 2. If you put n equal to, half. If you put n equal 3, that becomes 2 by 3. If you put n equal 4, that becomes 3 by 4. Goes like this. Right. So this is your n. So I'm writing your n here. So 1, 2, 3, 4, and so on. Okay. Now I am going to write my an minus 1, because we know that the sequence an converges to 1. That is why I am putting an minus 1. So if I try to calculate an minus 1, it is nothing. This is nothing actually. We know that 1 over n. Okay, this is nothing, 1 over n. So if you find 1 over n, so that means that this is 1, this is half, this is 1 over 3, this is 1 over 4, and so on. Okay, and so on. Now let me take my epsilon as, 0.25. Let me take my epsilon as 0.25. So the n I should select is the integral part of, so which is equal to, I know, 1 over 4. Okay, 1 over 4. So that means that 1 over epsilon, the integral part of 1 over epsilon plus 1. So which is equal to 4 plus 1. Okay, 4 plus 1. So that is 5. Okay, that is 5. So let me write some more terms here. So if you put this is a 4, I have put 0, 1, 2, 3, 4. If I put 5 here, then that becomes, if I put 5 here, that it becomes 4 over 5. Huh? So this is a fifth term. And here, if I put, that becomes 1 over 5. So my n should be 5. So look at here, the value of a n minus 5. So my n is 5. So you look at here. Now this is my n. So according to this calculation, this is my n. So you see here, the fourth one is 1 over 4, which is same as 0.25. This one is same as 2.5. After that onwards, if you look at all these values, okay, you can see that this value is less than 0.25. Okay, therefore there exists n. You have an n. You can find an n for that, for which all these terms after this particular n are less than this particular n. Therefore, we can say that this an converges to 1. Okay, so that is the meaning of this proof. We understand. We understand. Please respond to my question. Right. Okay. So I know that it is very logical and it is an analysis course. Therefore, you have to be, you have to read this carefully and try to understand. Actually, the thing that we are using here is the Archimedean property. It is not mentioned here. Okay, but you must know that it is not mentioned here. We are using the Archimedean property here to write this statement. Then we are saying that if we take n equal this one, then we can write this an minus n is less than 1 for all n greater than this one. Therefore, we can say that from the definition. Actually, here we are using the definition. Definitely, you will get a question like this. Okay, definitely will get a question like this. I will give you some tutorial question as well. Okay, I will give you some tutorial question as well. Right. Okay, now let's move to the next theorem. Actually, we don't want proof for this theorem. We don't want proof for this theorem, but you must know these things. Okay, so it says that we have two sequences. We have two sequences, an and the bn. The sequence an converges to a, as well as the sequence bn converges to b as n tends to infinity. Okay, so now we have a question. Okay, if an tends to a and bn tends to b, what will happen to the sum of these two sequences? What will happen to sum of these two sequences? Then we can prove that this sequence will converge to the value a plus b. Okay, if an converge to a and bn converge to b, then if you construct another sequence as sum of these two sequences, then you can show that the sum of this sequence will converge to a plus b. Okay, right. So that is first thing. Actually, you can use epsilon n definition. If you look at some textbook, they would have used this epsilon n definition to prove this theorem. So all these proofs they will use epsilon n definition to prove. Okay, so you can find out in some textbooks, or you can find on some websites. Okay, so please, if you have time, please try to Google and find the proof of this one. Okay, right. Now the next one is similar one. Here the sequence A converges to A and C is the real number. So the sequence A converges to A, and then you construct another sequence by multiplying this sequence A by a real number C. So our new sequence is C times A. Then this sequence will converge to the number CA. Okay, so that is also easily understood. Okay, the third one is, it says that the sequence an is less than or equal to bn for all n belongs to n. This is very important. Okay, here look at here. So every corresponding terms of the sequence an and bn, okay, if you compare every corresponding terms of the sequence an and bn, then the term of an is always less than or equal to the term of bn. So in that case, what will happen is, we know that an tends to a, bn tends to b, then if an is less than or equal to bn for all n, not for some n, for all n, for all natural number, then the limit value, if you have the if you write the relationship between the limit value of these two numbers, then you can see that a will be less than b. A will be less than b. Okay, so these are three basic results or theorems, okay, regarding the limit value of these sequences. And the last one is very, very important. So definitely in your final exam, you will get a question applying this last theorem, okay, because this is one of the famous theorem, under the topic of sequence, okay. Therefore, definitely, if you see any past paper, definitely you can find a question from this section, okay. So proof is not necessary, but you must know, at least you must know to state this theorem, okay. Sometimes they may ask you to state this theorem. This is called the sandwich theorem. This is called the sandwich theorem. There is another name for this one, that is called the skews theorem. There is another name, skews. Okay, skews theorem. There is another name for this theorem. It's called the skews theorem. Okay, let me explain what is sandwich theorem talks about. Okay, right now. It says that we have three sequences. We have the sequence AN, we have sequence CN, we have sequence BN. But that sequence satisfies this condition for all n belongs to n. For all n belongs to n. Then, okay, so AN is less than or equal to BN, less than or equal to CN for all n belongs to n. For all natural numbers, for all natural numbers. Then we have another result, that is the sequence AN tends to A, the sequence CN tends, the sequence, sorry, let me have the sequence CN in the middle. It's nothing, just since I have already defined AN and BN on the top, let me write it in this way, okay? So AN is less than or equal to CN less than or equal to BN. Let me write it in this way, okay? Let me write it in this way. Now we know that this sequence AN tends to A and this sequence BN tends to B. But what we know about A and B is A is equal to B. A is equal to B. This sequence tends to A, this sequence tends to B. But these two values are equal. Then what will happen is, okay, what will happen is the CN also tends to A because it's a common value, because it is in the middle. That is why we are saying that sandwich theorem, because this CN is in the middle. Okay, so you have a slice of bread here, you have another slice of bread here, here you have the mixture. Okay, this is your sequence CN, this is your sequence AN, this is your sequence BN, or you can write it other way also, no problem. This is your sequence AN and this is your sequence BN. Okay, so this goes to B, this goes to A, but these two are equal. Then what will happen? This one, this also will go to one of these, okay, because they are equal. So that is why it says sandwich theorem. Okay, so this is a really important and useful theorem to find out the limit value of some sequences. Okay, let's have this example to understand a little further. Okay, so here we understand this theorem. Do you understand this? Yes or no? Please respond. Do you understand? Hello? Can anyone answer me?
Yes, sir.
Okay. Right. So now consider sequence AN with AN equal 1 plus 1 over n to the power 1 over n. Then we have to show that limit AN tends to infinity equal to 1. Okay. So hint is given here. Hint says that observe that 1 is less than or equal to a less than or equal to 1 plus 1 over n 4 over n. Okay, so the question is we want to find out the limit of 1 plus 1 over n 1 over n. Okay, n tends to infinity equal 1. This is what we want to prove it. Okay, here we are going to use the Skews theorem to show that this converges to 1. Here we are not using the definition. If you try to use the definition, sometime it will be difficult. Okay, because it involves therefore sometimes it will be difficult if you try to use the epsilon n definition. That is why here we are going to use the sandwich theorem. Okay, as one of the application of sandwich theorem, you can see this question. Okay, right. Now here what we are going to do is we are going to find two sequences. We are going to find two sequences such that this sequence is less than one sequence and greater than another sequence. Okay, so I am going to find out two sequences. I'm going to find out two sequences. Say I'm going to find out two sequences. Say xn, which is less than the given sequence a or less than or equal. This is less than or equal. I'm going to find another sequence yn which is greater than this a. Then if I show this xn tends to 1 and yn also tends to 1, then what can I say about the limit point of this one? Then I can say that this also tends to 1. Therefore, I want to find two sequences. So I want to do some guess. Okay, I want to do some guess for xn and yn which satisfy this condition, and they are somewhat simple sequence. Okay, this is somewhat complicated sequence. Why? This is somewhat complicated sequence because it involves power. Therefore, we are going to find out, or we are going to do some guess to find the sequence xn and yn such that xn is less than or equal to an less than or equal to yn. Meantime, xn tends to 1, yn also tends to 1, so that using the sandwich theorem, we can say that an tends to 1. Okay, so that is the idea here. But here it is given. So they are telling that take your xn as 1, take your xn as 1, take your yn as 1 plus 1 over 1 plus 1 over. Then obviously we know that 1 is less than or equal to, okay, 1 is less than or equal to 1 plus 1 over n to the power n less than or equal to 1 plus 1 over n. Okay, so actually we want to prove this one. First we want to prove this one. We want to prove this one first. Okay, then using this result, okay, using the result, what you can say, if you take limit 1 n tends to infinity is less than or equal to limit n tends to infinity, okay, 1 plus 1 over n to the power 1 over n is less than or equal to limit 1 plus 1 over n tends to infinity. But we know that what? Limit n tends to infinity 1. So this sequence is independent of n. Therefore, value of this one is 1. Less than or equal to limit 1 plus limit 1 plus 1 over n to the power 1 over n tends to infinity is less than or equal to, when n tends to infinity, this term becomes 0, therefore this is also 1. Therefore, you see that here, the limit of this sequence lies between 1 and 1. So what can I say now? Using the sandwich theorem, this also goes to 1. So that is the idea. Okay. So here, if you want to show like this, what we have to do is we have to prove this inequality. We have to show that 1 is always less than or equal to 1 plus 1 over n to the power 1 over n less than or equal to 1 plus 1 over n for all n belongs to n. So we have to prove this one. So once we prove this one, we can use this inequality to prove this one. Okay, so here this is nothing. Here this is nothing actually. So you can say that from sandwich theorem. From sandwich theorem, you can say that this sequence converges to 1. Okay, so that is nothing. So actually here, this part, you want to prove this one. So how you can prove this actually? 1 is less than or equal to 1 plus 1 over n to the power n less than or equal to 1 plus n. How you can prove this? So let me prove this one. You can use mathematical induction to prove this one. So 1 is less than or equal to, you want to prove 1 is less than or equal to 1 plus 1 over n to the power 1 over n less than or equal to 1 plus 1 over. Okay. So this is what you want to prove. Now let's use mathematical induction or some mathematical facts. So proof. So we know that 1 is always less than or equal to 1 is always less than or equal to 1 plus 1 over n. Isn't it? So that is very true because 1 is always less than or equal to 1 plus 1 over n for all n belongs to n. Because the right hand side is somewhat larger than the left hand side because we are adding 1 over n to 1. Okay, therefore definitely this one is greater. Okay, so definitely this one is greater. Now since both are positive, both sides are positive, what you can do is you can consider any power both sides. So if you take 1 to the power n is always less than or equal to 1 plus but we know that 1 to the power 1 raised to the power any number is always 1. So this is 1 is less than or equal to 1 plus 1. So that is done. So this part, the first part of this inequality is done. So actually now we want to prove only this part. We want to prove only this part. Okay, let's prove that also. Let's try to prove that also. Hope you understand this. You understand this one? Hello, do you understand this too?
Yes, sir.
Yeah, yes, okay, fine. So now we'll prove the second part of this proof, that is 1 over 1 plus 1 to the power n is equal to 1 plus 1 over n. Okay, so you want to prove, you want to show. So 1 plus 1 to the power n is less than or equal to 1 plus 1. Okay, so we know that, look at here, we know that 1 is less than or equal to 1 plus 1 over n. This is true. Now I am going to take the power n minus 1 both sides. I am going to take power n minus 1 both sides. So if I take power n minus 1 both sides, so 1 to the power n minus 1. Okay, 1 to the power n minus 1 is less than or equal to 1 plus 1 over n to the power n minus 1. Okay, now since 1 plus 1 over n is a positive number, 1 plus 1 over n is a positive number, I am going to multiply this inequality by 1 plus 1 to the power n both sides. I am going to multiply this inequality by 1 plus 1 over n both sides. Okay, I am going to multiply because that's a positive number. Okay, it's a positive number. Therefore, if I multiply this both sides, the inequality will not alter. Therefore, if I multiply this by this side, so we know that 1 to the power any number is 1. Okay. So if I multiply that, I will get 1 into 1 plus 1 over less than or equal to. And you see, I'm multiplying by the same, but we have the right hand side. Therefore, this will become 1 plus 1 over power n to the power n. Okay. So now if I take the nth root, if I take the nth root, what will happen? 1 plus 1 over n to the power 1 over. This time also inequality will not alter. Then if you take nth root of this right hand side, that will become 1 over 1 plus. So let me say this is my second relation, and let me say this is my first relation. So combining first and last from 1 and 2. Okay. So I can write combining 1 and 2, I can write 1 is less than or equal to 1 plus 1 over n. So now if I apply the skews theorem, then if I take limit both sides, limit 1 n tends to infinity is less than or equal to limit 1 plus 1 over n to the power 1 over n tends to infinity less than or equal to limit 1 plus 1 over n. Okay, so this is actually goes to 1 less than or equal to limit 1 plus 1 over n to the power 1 over n tends to infinity is less than or equal to, as n tends to infinity, this becomes 1. So from the skews theorem or from the sandwich theorem, you can say that limit 1 plus 1 over n to the power 1 over n as n tends to infinity equal to. You understand? Hello, do you understand this?
Yes, sir.
Okay, fine. Right. Now that's all about that's end of handout number 3. Let's go to handout number 4. There's a similar question here. Okay, so please carefully try to do this question. Okay, I give this as a homework, but I'm saying please try to practice this question. Please try to practice this question. Okay, so here a comma b are real number, and 0 less than a less than b, then limit n tends to infinity a to the power n plus b to the power n to the power hold in 1 over n equal to b. Okay, so for this one also you can use skews theorem. Okay, for this one also you can use the skews theorem. Right. So now we'll go to the next definition, definition 2.2, divergent sequence. Now so far we know that what is convergent sequence. Convergent sequence means if a sequence an tends to a finite number, if a sequence an tends to a finite number a as n tends to infinity, then we say that that sequence is a convergent sequence. If it is not convergent, if the sequence does not go to a finite number, okay, the sequence does not go to a finite number, then we say that that sequence is a divergent sequence. So actually the sequence that are not convergent, okay, the sequence that are not convergent, we call it as the divergent sequence. The definition is very simple. Okay, so now there can be two types of divergence. Okay, there can be two type of divergence. One we call it as a divergence to plus infinity, and the other one is divergence to minus infinity. So when we say divergence to plus infinity, we'll look at now. When we say the sequence diverges to plus infinity, and when we say that the sequence diverges to minus infinity. Okay, so if an is such that for every m greater than 0, there exists n belongs to n such that an is greater than m for all n belongs to n, then we say that an diverges to infinity. So that means that you have the sequence a1, a2, and so on. Okay. Then if you choose any m, okay, if you choose any m, capital M, any number, any capital, any positive number, say your m is equal to 1500. Then if you have a sequence, okay, if you have a sequence, say you have a sequence here, all these values, the values of the terms, all these values are greater than this capital M. Okay, greater than this capital M. Okay, then we say that this sequence diverges to plus infinity because there is no bound for this sequence. Okay, even whatever the number, even if you say m is equal to 100,000, if you pick m as 100,000, then there will be a point. All the values after that are greater than m. Then such sequence we call it as we say it diverges to plus infinity. Okay. Similarly, here we say that the sequence diverges to minus infinity. So we say that the sequence diverges to minus infinity if there is uh, if there is uh, yeah if there is capital M positive number such that an is less than or equal to minus n for all n. So in that case, we say that this sequence converges to minus n. So that means that here, look at this definition. So you have the sequence say a1, a2, a3, and it goes like this. Okay. Now you choose your m as say 999. Whatever the number you can, whatever the positive number you can choose, whatever the positive number you can choose. Then there is a capital N. There's a capital N. Okay. From that onwards, all these values are less than minus 999. Okay. So what is happening here? It goes towards negative infinity. Here, what is happening? This goes towards plus infinity. Okay. Here, what is happening? This goes towards minus infinity. So therefore, we say that diverges to minus infinity. Okay. So that is the definition of diverges to plus infinity and diverges to minus infinity. Now we are moving to another important thing. Okay. So we are moving to another important thing. So under the sequence, three things are very important. First one is epsilon n definition. Okay, you must know how to apply epsilon n definition to show the particular sequence converges to particular number. The second important thing is the sandwich theorem. Okay, sandwich theorem, because sandwich theorem is one of the very useful theorem under the sequence. Okay, sandwich theorem. The third one is bounded sequence, because based on the bounded property, okay, based on the boundness of particular sequence, we can talk about the critical. There is a connection between boundness and convergence. So that is why this takes important place. This also takes important place, boundness. So let's read the definition. What is it? Bounded above, bounded below, bounded sequence. Okay, so we have actually studied similar things in chapter 1 also. So when we study real number system, we studied that set S is said to be bounded if we have upper bound. Okay, a set a set S is said to be bounded below if it has a lower bound. Then we say that the set is bounded if we have both upper bounded, if it is both bounded above and bounded below. Similarly, the similar definition we have here. It says that a sequence AN is said to be bounded above if there exists a real number capital M such that AN is less than or equal to M for all n belongs to M. So this sequence, okay, if sequence is less than or equal to a finite number for all n. So what is happening here? The sequence, the values of this sequence is bounded by a particular number. Okay, so in this case, this sequence AN, we call it as the bounded above. Okay, so the counterpart of this bounded above is bounded below. The counterpart of bounded above is the bounded below. What does it say? It says that if you have a real number M dash, okay, for which, okay, the AN is, yeah, sorry, right, sorry. So it says that for AN, there is a real number right. It says that you have a real number M dash. Okay. So for which this AN is greater than that particular M dash. Okay. So in that case, we say that that sequence is bounded. Okay. So if a sequence, okay, if a sequence AN is less than or equal to some capital M, then we say that the sequence is bounded above. The sequence AN is greater than or equal to some finite number capital M dash. In that case, we say that the sequence is bounded below. If it is both, if a sequence is bounded below and bounded above, that means that a sequence is between two numbers, capital M and simple M, or you can say capital M and M dash. Okay, it is bounded both sides, bounded above and bounded below. Then in that case, we say that the sequence AN is bounded. Okay, so in this sequence AN is bounded. Okay, so that's all for today. And tomorrow I will start. I will do integral transform. Actually, I